This chapter is all about fluid mechanics. Now, a fluid is something that has the ability to flow. We're going to be looking at two different things. We're going to look at liquids and also gases. Yes, gases can flow. So we're going to look at those two ideas, not necessarily solids for this particular chapter. Now, to start this, to be able to look at how fluids are going to react, we're going to look at two different concepts, density and pressure. Density is defined as a measure of compactness, how much stuff is in a certain volume. The equation is density equals mass divided by volume. So what units does that have? Well, mass is generally given in grams or kilograms, pounds, even though pounds is technically a weight, not a mass. We still sometimes will see that. Volume could be milliliters, liters, gallons. So generally the units that you're going to see are going to be grams per milliliter for this class, but there's many other units that you might see, any type of mass divided by whatever type of volume that you're looking at. So what we want to do next is we want to look at some just normal densities of common objects. Now I know that you've heard before that if you compare muscle and fat, that muscle weighs more than fat. Well, technically it's more dense. If you look at the certain volume of either muscle or fat, there's more of that muscle in that volume than there is fat. It has more mass associated with it. So that's why if you're very muscular, you're more likely to sink, while someone who has a little bit more, well, let's just say not muscle, is a little more likely to float. Now, how much truth there is to that, for most people it's not going to make much of a difference, but I have talked to people who have found it very, very difficult to float because they had such a low body fat percentage in their body. So let's get back to these densities of common objects. The one that we use to compare to almost everything else is water. Water is defined as having a density of 1 gram per milliliter. And if you get into how they define what a milliliter was, well, it goes back to water also. Water is very commonly available. It's a great thing to use as a standard. Now, some of the other things, you can look at gold. Gold has a much higher density, 19.3 grams per milliliter. Now, this is one way that they are able to distinguish between true gold, real gold, and fool's gold. If you go back to the gold rush in California many, many years ago. And if you think of how they try to get gold, they pan for gold. So they dip their pan into a stream. They have water in there and dirt and small rocks and hopefully some nuggets of gold. Like I said, hopefully. And then they swirl it around, putting more water in it. That water is going to wash away the less dense substances and leave the things that are very dense or very sort of heavy, and I put that heavy in quotes. Technically not heavy, it's very dense. And that's going to leave your gold there on the bottom. Iron is between water and gold. It's about 7.8, and aluminum is 2.7 grams per milliliter. Now, aluminum is very important because, of course, today we use aluminum for a lot of our packaging. If you think of aluminum cans for your soda pop, the reason they're going to use aluminum is because, well, it does have that lightweight density. It doesn't cost as much to transport it. Based on these densities, they're very unique for those substances. We can use the density of an object to help determine what it is. Density is an intensive property. Now, I don't know if we've talked about that term before, intensive property. What it means is that you have something that's independent of sample size. It doesn't matter if you have a small sample or a large sample, this value is always going to remain the same. The opposite of that is an extensive property, extensive. That means that it does depend on the size of the sample. Well, if you look at the equation on how you get density, density equals mass divided by volume. Both mass and volume are extensive. It really depends on the sample you get. One's going to be slightly larger than the other. But when you take that ratio, when you divide those two, it becomes intensive. Again, it doesn't matter if you have a small sample or a large sample. this value is always going to remain the same. That's why we can use it to identify an unknown metal. And if you took the class on campus with me, you would actually have a lab to where you would have to do that. You would be determining the densities of different metals and then trying to figure out what an unknown sample was. Now, another concept of fluids is pressure. Pressure is defined as force divided by area. Let me give you a few examples. Ladies, or if you're a man, sorry, I'm going to use a lady as an example here. Would you be more likely to see them, if it's really muddy out, wearing flats or high heels? Well, the answer is that they would be wearing flats, and the reason for that is because they're less likely to sink in the mud or in the snow. This is the same reason why you would use snowshoes. Snowshoes have a really big area. So why is that? The force is the gravitational pull on the person, their weight. That force does not change if it's on dry land or if it's on muddy land or if it's on snowy land. The force is the same. But what we can change is the area. Now, if you go from high heels would have a very, very small area, to flats or snowshoes, you increase the area. As you increase the area, you actually decrease the pressure. Another example of that, pick up a pencil or a pen. Using the flat end, the eraser end of that pencil, apply a certain amount of force to that pencil against your hand. You can feel the pressure. Now, if you were to turn it over and use the sharp end, you could apply the same pressure, the same force, and feel a very different pressure. Now, I'm not recommending that you do that. I don't want you to call me and say, "Oh, Miss Lumley, I did that, and now I have lead stuck in my hand." Don't do it that way. But that's the idea of pressure, to kind of let you think about that. Now, what units is pressure measured in? Well, first we have to see about force. We talked about force in a previous chapter. Remember, force equals mass times acceleration. The units on it, well, mass is in kilograms, acceleration is in meters per second squared, so force itself is in a unit called a Newton. Remember, they came up with this new term, Newton. And Newton is approximately the same as the gravitational attraction acting upon an apple that you hold in your hand. Because remember, Newton got hit in the head, right? With an apple, and that's how he figured a lot of this stuff out. Now, if you take that force, the gravitational force acting upon an apple, and you spread it over a meter squared, so a meter is about a yard, about the span of from your thumb to your nose, that's a pretty big area. So this has a new name. It's a Newton over meter squared, and they call it a Pascal. Pascals are very, very tiny. Another example is the pressure of a dollar bill sitting on a flat surface. So it's not very much. Because a Pascal is so small, most scientists will use other units, such as kilopascals. Some other units that you'll hear: atmosphere, torr, pounds per square inch, or psi, millimeters of mercury, and bar. And we'll talk more about those throughout this chapter. Liquids exert a certain amount of pressure. Now, this is due to the weight of the fluid, of the liquid, that's directly above you. So you have the weight of the water, plus you have the weight of the atmosphere. Yes, the atmosphere has a weight. If you can imagine, there's all these little air molecules that extend up miles over the surface, and each of those air molecules has a gravitational attraction to the Earth due to the size of the Earth. They all have a certain force associated with that over a certain amount of area, and you've got a pressure. We're going to talk more about that gravitational attraction here in a few minutes. Now let's go back to the weight of the fluid. Now, as you go deeper, so as you swim in deeper water, there's more fluid above you, and therefore you have more pressure that's associated with that. If you can imagine a submarine, or if you could go to the bottom depths of the ocean, the pressures down there are absolutely enormous because there's so much water above them. And in addition to that, then you also have the atmosphere. Now, it turns out this pressure does not depend on the volume of liquid. What it depends on is the depth. So the same pressure is experienced at 1 meter in a large body of water versus a small body of water. And that's what the diagram on the bottom is supposed to show. Here we have two dams. We have a large but shallow lake where the dam is only 3 meters, versus a small but deep pond, which is 6 meters. And it turns out that the pressure experienced by the deep pond is twice as much as the large but shallow lake, and that's because of the depth of that water. Now, pressure is exerted in all directions, up, down, and sideways. And the up pressure is something very special, and we'll talk about that later in this chapter. Now here's a cup filled with water with 3 holes cut into it. And what we're looking at here is how the pressure is different depending on the depth. Remember, the water at the top of the cup and the bottom of the cup experience different pressures because they are at different depths. As the water goes through the holes, it moves horizontally until it's acted upon by gravity, which causes it to curve downward. At greater depths, the water moves faster due to increased pressure. It actually has more force, which is illustrated by the longer vector lines. Remember, those vector lines are the little pink lines at the bottom of the cup versus the top of the cup. So the bottom of the cup has more force, we have more pressure. Notice at the bottom of the cup also, the water moves in a more horizontal fashion because it's moving faster. So it actually goes further out before gravity has a chance to pull it down. Remember, pressure is exerted in all directions on an object. For this illustration, we have a rock that's submerged in water. There's pressure pushing against all sides of it, on the top, on the sides, and on the bottom. If you notice, at the top we have small vector lines, and at the bottom we have larger vector lines. Well, why is that? Well, at the bottom, it's deeper in the water, so there's more pressure that's pressing up than there is at the top pressing down because it's in shallower water. Now, that upward force has a special name. It's called buoyancy, or the buoyant force. Now, if you notice on the sides, the vector length is between the top and the bottom because it's in the water that's in between the top and bottom at different depths, and they're equal on both sides. That means that there's not going to be a force that pushes it side to side. We have this force that's pushing it down and a force that's pushing it up. The downward and the upward force are not equal to one another, and that's the reason why you have some things that will float or sink. If the buoyant force, the upward force, is greater than the weight of the object, so if the buoyant force, the upward force, is greater than the weight of the object that you are looking at will float. If the weight of the object is greater than the buoyancy force, it's going to sink. And we actually get to talk more about that here in a few minutes. If the buoyant force and the weight are equal to one another, that object will actually stay suspended. Have you ever noticed when you fill a bathtub with water and then you step into it, the water level rises? Or when you step out, the water level actually drops? It turns out that there's a relationship between the amount the water moves, the volume of water displaced, that is, and the object that you place in the water. A completely submerged object will displace a volume of liquid equal to its own volume. So if you place a rock in the water, it displaces the same volume of water. Now, legend has it that the guy who came up with this was a Greek philosopher by the name of Archimedes. He was given the task of determining if a crown was truly made out of gold or if it was some other metal. So he was going to look at the idea of density to help him with this. But what he had was a crown, and he couldn't destroy it and make it into a nice, regularly shaped object. So he had to find some other way to determine the volume of this crown so he could determine what the density was. Now, supposedly, he made this connection when he was at a public bathhouse, and he was noticing that when people stepped in, they displaced water, a certain amount or certain volume of water. Now, this excited him so much, legend has it, that he started running through town completely naked, screaming, "Eureka! Eureka!" or "I found it! I found it!" Now, it turns out that particular crown was not made out of gold. Again, that's how the story goes. But what we're going to do is we can actually determine the volume of an object by measuring the volume of water that's displaced or changed whenever we submerge an object. Now Archimedes went on, after figuring out that the volume of an object displaces the same volume of a fluid that it's placed on, to come up with what we call the Archimedes principle. What this states is that an immersed body is buoyed up by a force equal to the weight of the displaced fluid. So let's talk this through. Remember, when an object is submerged, it displaces the same volume of liquid. Archimedes states that the weight of that liquid, in this case we generally talk about water, that's displaced is equal to the buoyant force, or the upward force that's pressing up against that object. Now, what we have here is an example with a block, and it's attached to kind of like a tension scale or a fish scale, if you want to call it that. And what we find is that the block, if it's not submerged, has a weight of 3 newtons. Now remember, newton is just the SI version of a pound. They're different numerically, but it's the same idea. It's a force. Here we're looking at the gravitational force acting upon it. Now, if we submerge that block, it displaces water. That displaced water has gone to the other scale. And what you find is that however much the weight of the water that was displaced is equal to the upward force pressing up on that object. So now the apparent weight of that object once it's submerged is 1 newton. The water that's displaced is 2 newtons. When we add those together, it equals the 3 newtons that we'd actually started with. So apparent weight plus the buoyant force is equal to the weight of an object outside of water. So how can we make something that's density is greater than water actually float? This is called the principle of flotation, and we'll get into this one here over the next few minutes. What it states is that a floating object will displace a weight of fluid equal to its own weight. Well, let's look at the examples. The examples are better. We're going to start with the canoe, and then the canoe with the hippo. The canoe has a certain weight. It's floating. However much weight it's pressing down, it has to have a buoyant force that presses up. And remember, the buoyant force is equal to the weight of the liquid it displaces. Now, when the hippo sits down in the canoe, it goes down further. It weighs more. It has to displace more water. That's why it's going to sit lower in the fluid than it did before. Now, another example is on the lower left-hand side. What we have here is an example of iron. Now, iron itself, if you think of a block of iron, it's going to sink. Its density is greater than water. It has a density of like 7.8 or something like that. Water is only 1.0 grams per milliliter, so it would sink. But what you can do is you can change the volume of that iron. You can make it into a bowl-shaped structure. When you do that, it displaces more water. When it displaces more water, you have more of a buoyant force. Notice that the vectors on the 2 buoyant forces between the block and the bowl-shaped structure. This is also how big ships work. What we're going to do is we're going to displace larger amounts of water so that that object can actually float. For example, if a ship weighs 10,000 tons, it must displace at least 10,000 tons of water. That's generally why they're built very wide, so they can displace more water. This is the idea behind the aluminum boat challenge. What you're going to do is try to build an aluminum boat out of aluminum foil and see if you can make it float. Now, after you do your experiment, try this. Take that aluminum foil, crumple it up in a ball, and put it in the water and see what happens. Does it float anymore? Now what we're going to do is we're going to switch gears slightly and start talking about gases. Because remember, a gas is a type of fluid. And we're going to start with a relationship described in Boyle's law. Now, I like to tell you a little bit about the scientists. I think it helps us understand what was going on and how they came up with these ideas. Robert Boyle was an Irish natural philosopher in the 1600s. He was the first to make careful scientific experiments /notes/logs he wrote everything down. He was very careful about his measurements, and he really spurred this scientific um, era that was coming on. Now, a little bit about his background. He was the 14th child out of 15. Can you imagine that? Having 14 brothers and sisters? His mom died in childbirth when he was 3, and his dad was killed in a war when he was only 12. He had to overcome a lot of great odds to be able to later go on and establish this particular relationship. Um, this relationship is also sometimes giving credit to a French um, physicist but it was about 15 years later before he actually published it. So we'll just call it Boyle's Law. This was first published in 1662. Let's see here. So what it states is that if you increase the pressure, you decrease the volume. You actually have a lab that deals with this. This is a really great lab. You use a syringe and a marshmallow. It's fun to do. So try that one out. Now this is assuming that T, or temperature, is constant. So over to the side, we're going to have this relationship. Now, if you can think of a gas as being these little air molecules that bounce around in a chaotic motion, random chaotic motion, they hit each other, they hit the sides of the wall. As they hit the sides of the wall, that's where the force comes from for the pressure. So the more they hit the sides of the wall, the more pressure there is. And then we could also, with the pressure, you also have to look at the area it's occurring over. So on the top, we have a certain volume and a certain pressure that's being exerted due to the force of those little molecules hitting the walls over a certain area. Then what we're going to do is we're actually going to decrease the volume. We're going to make it go into a smaller area. Well, when you do that, those little gas molecules are still bouncing around, but now there's more walls, so to speak. There's not as much empty space in between things. All of a sudden, they keep hitting these walls. That increases the force. We've also decreased the area, so the pressure is going to jump up. This applies to what are called ideal gases. Ideal gases means that it follows Boyle's law. The opposite of an ideal gas is a real gas. A real gas is how a gas actually behaves, kind of like an ideal student and a real student. They don't always behave in the same fashion. But in general, they do things very similarly. Same is true for gases. In most cases, a real gas will act as an ideal gas until you get to really high pressures or really low temperatures. Now, using Boyle's law, we can establish a relationship. There's an equation that says P1V1 equals P2V2. Now, don't get scared about the equation. All that it's trying to say is that the pressure and the volume are in some way related. If you increase one, you decrease the other. You can have a before and after scenario. So P1V1 is the pressure and volume of your first scenario. In this case, up on top where we have a larger volume, a lower pressure. We change the volume and we see what happens to the pressure. Or you change the pressure and see what happens to the volume. There's some sort of relationship between those. In 1654, before Newton's third law was published, a gentleman by the name of Otto von Guericke, who was Burgermeister, he was like a town mayor of a town called Magdeburg, demonstrated that the atmosphere exerts a certain amount of pressure. This is the same guy that invented a vacuum pump. What he did is he took a leather ring that was soaked in oil and wax to make it airtight, and he placed it between two copper hemispheres. These copper hemispheres were about half a meter in diameter. And then he evacuated the air. He took the air out from between the hemispheres. And what he found is that two teams of horses could not pull those hemispheres apart. They weren't bolted together. They were just held together. Just two copper hemispheres and this leather airtight seal between them. So how did it work? When the two hemispheres were together initially, before they evacuated the air, there's atmospheric pressure pushing them together, and there's air inside pushing them apart, so it's easy to separate. When the air was removed, there was still atmospheric pressure pushing them together. But there's not air molecules inside trying to force them apart anymore. No little air molecules inside bouncing around trying to to add force or pressure to make them go apart. So the atmosphere was actually holding them together. Another application of this is the little suction cup that you see in the corner. Now if you think about what we're going to try to do is we're going to try to lift an object. Say maybe a table. So if you think of a table, there's a certain amount of pressure pressing down on the table, and there's a certain amount of pressure pressing up, because remember, pressure is exerted in all directions. Then what we do is we put this little suction cup and we just lay it on the top. Okay, so now we have the table, pressure underneath, pressure on top. We have the suction cup. The suction cup has pressure underneath and pressure on top, just like the table does. Well, we put the suction cup on the table and we engage the handle. So what that does is it forces out all of the little air molecules that are between the table and the suction cup. So if we look in between there, there's no pressure pushing up or pushing down. So what you can do is you can actually lift with that suction cup. Whenever we say lift, it just means that there's less pressure pushing down on that table, but there's still an upward force pressing up against the bottom of the table, and so it makes it to where it's easier to lift. Kind of a cool little thing. That particular picture is from Harbor Freight. If you have one of those, that's kind of a cool little tool store to be able to go into and buy some cheap stuff. So our atmosphere presses down with a certain pressure. Now that pressure is due to the weight of the atmosphere, the gravitational attraction of all the little gas molecules that are between you on the surface of the Earth and the outer reaches of our atmosphere, which actually isn't as far as you think it might be. We got to talk about that later. Now our bodies are adapted to this. We don't realize that it's there. If you were to go mountain climbing, you want to go to the top of Mount Everest, you know, or you've heard, that the air at the top is not as thick, or it's thinner than the air at the bottom. Well, the reason for that is that the density of air depends on the altitude. The higher up you get, there's less gravitational attraction because you're further away from the Earth. There's fewer gas molecules. Now, pressure at any surface is not uniform. So if I'm sitting here in Coffeyville, Kansas, the pressure is going to change day to day. Not very much, just a little. Those changes in pressures are explained using meteorology. You have fronts moving in, so a cold air front or a warm air front. You have storms that come in. Hurricanes, they talk a lot about pressure also. And we'll get to talk more about that whenever we get to meteorology. Now let's look at this little picture. So here we have a little dude sitting on the surface of the Earth, and there's a cane that's sticking up. It's supposed to represent a bamboo cane. And on the inside, it's hollow. Now it has a certain amount of pressure that's pressing down on that inside. Now it turns out that if you had something that was an inch square that extended all the way to the top of the reaches of our atmosphere, it would have a weight or gravitational traction pulling down of about 14.7 pounds. That's where that 14.7 pounds per square inch comes from. That's atmospheric pressure, the amount of pressure that's pressing against every square inch of your body. Now, if we want to look at meters squared, that's about 100,000 newtons. Now remember, a newton per meter squared is a pascal, so that's about 100,000 pascals. Now, because pascals are so small, they'll say it's about 100 kilopascals. Actually, 101.324 kilopascals to be exact. And that is your standard atmospheric pressure. Now what we've done is we've given it a couple of different terms that make it a little bit easier to work with. We also can call it one standard atmosphere or 1 bar. A barometer is an instrument used for measuring atmospheric pressure. Now how this was originally developed, made, however you want to consider it, was they took a glass tube that was closed on one end. In this glass tube they completely filled it with mercury, which is a silvery liquid. It's actually metallic. They used to use it in thermometers and barometers and your blood pressure cuffs, but we've stopped using it a lot of times because it is toxic. So don't go out and play with mercury. But that's what they did to start this. They filled a tube completely filled with mercury, and then they quickly turned it upside down into a pool of mercury. We have a couple of different things going on. Number one, in the tube, mercury is being pulled down because of gravity. Now, you would think that might completely empty out, but it doesn't. But what they found is only a certain column, a certain height, could be established, and that height is 760 millimeters, or 76 centimeters, or 0.76 meters, about 3/4 of a meter. Now, why is that? Why doesn't it completely come down? Well, if you look at the pool of mercury surrounding that glass tube, you can see there are some forces pushing down on it, and that is due to atmospheric pressure. So you have gravity pulling the mercury down the tube. You also have atmospheric pressure pressing against the pool, pushing mercury back up into the tube. Now, that height that's established, that 760 millimeters, is what they found the height to be at sea level. Now, it will change slightly depending on the day, what type of weather you have coming through. Now, you could do the same thing with water, and this is actually, the story goes, this is how this idea actually developed. They were trying to have water go up into this like a second story or third story house, and they could never get the water column to be supported above a certain height. Now, for water, because water is so much less dense than mercury, that column is actually 10.3 meters high. Now think about that, 10.3 meters versus 3/4 of a meter. That's due to the different densities. So we do not use water for a barometer because it would have to be too tall. But you can get the same idea. We use mercury because it's so dense, and therefore it would be fairly short. Now back to that idea of atmospheric pressure. So we have all these little gas molecules all around us pushing down with some amount of force. That's actually how straws work. Straws do not work by sucking up the liquid. What you actually do is you reduce the pressure around there. So by putting your mouth on it, it allows more area for the little gas molecules to go. And then what happens is the atmospheric pressure, which is designated by this little fist, pushes down on the liquid, which forces it up the straw. This is why if you get a hole in your straw, it doesn't work as good, because you can't reduce the pressure in the straw itself. Now what we're going to do is try to use the idea of pressure to be able to be useful to us. And to do that, we're going to use something called Pascal's principle. Now, as you can imagine, this is one of the scientists who did a lot in this area, and they actually named the pressure unit Pascal after him. Now keep in mind, if you apply a certain amount of pressure, that pressure will be the same throughout, and that's what the definition is trying to state. A change in pressure at any point in enclosed fluid is at rest. Now all of this is at rest. We'll talk about in motion in a few minutes. It's transmitted undiminished, so it's not going to drop, to all the points in a fluid. So here we have an example. If you are pumping water from a pumping station, and you increase the pressure of that water by 10 times, then the pressure of the water in all the pipes connected to the pumping station will also increase by 10 units. If you change the area, this is whenever it gets really important, you can actually multiply the force. But this changes the distances that are covered, so it does not violate the conservation of energy. So let's look at our example. On the bottom left is just to show you if you increase the pressure on one side, it increases the pressure all throughout. On the other side is when we can change the area and get more load, you could say, out of it, even though the distance isn't going to be as great. So we can multiply force when we change the area. For example, if you put a 10 kilogram load and place it on a piston, the additional pressure is transmitted to the rest of the fluid. If the other piston is 50 times larger, the area that is, it can support a load that's 50 times greater. So in this case, 500 kilograms. So you start with a 10 kilogram load, and you end up being able to support 500 kilograms. We were able to multiply the force. However, because it's a larger area, it's not going to move as far. It's only going to move about 1/50th of the distance. Now, one application that you may have seen this used before is whenever you take your car in and they use a hydraulic lift to lift it up. In this case, they're going to increase the air pressure using an air compressor, which pushes on a reservoir of oil. Notice we have a large area that is going over. The increased pressure is transmitted to a piston of smaller area, which causes it to lift the automobile. Because it's a smaller area, it's actually going to move more than the reservoir is going to move. They say it really doesn't take that much extra air pressure. About the amount that you would air up your tires is all they're going to have to place on that reservoir of oil to go ahead and lift your car up. Now remember, this entire chapter is all about fluids, and fluids include liquids and gases. This particular slide talks about the buoyancy in a gas. And we talked about buoyancy before. We said that if you are in water, the deeper you go in the water, the more force you're going to feel, and that upward force is called buoyancy. We can also look at gases the same way. Now, an object surrounded by air is buoyed up by a force equal to the weight of the air displaced. It turns out that this force on air, 1 cubic meter of air is about 12 newtons. That's its weight. So if an object weighs less than 12 newtons per meter cubed, if its density is less than that, it will actually float. If it weighs more, then it's going to sink. So here we have a hot air balloon. And so what you have to do is you have to have the density of the air inside to be less than the density outside so that the buoyancy force can go ahead and lift that up. Bernoulli's principle deals whenever you have motion of a fluid. Before we were talking about stationary. Now we have some motion that's occurring. Remember, fluid is both liquids and gases. What it states, more or less, is that if you have a fluid going through a pipe and you decrease the diameter of the pipe, that fluid goes faster. Now, you guys have seen that before in streams, going through pipes. This is something you've probably observed. Maybe you really hadn't thought about it. Now, the interesting thing is, as the speed actually increases, the internal pressure decreases. Now, that was kind of hard to wrap your mind around, because if you step in a stream that's moving really fast, you know that there's a lot of pressure pressing against you, and you can actually fall quite easily, and that's why they say you're not supposed to drive a vehicle if a road is flooded. But what that is you're actually trying to stop the flow of the fluid. That's an external pressure type idea. The internal pressure actually decreases. Now, this can be seen if there's air bubbles. As it goes to the narrower part of the pipe and the speed increases, the air bubbles will actually increase in size due to that decreased internal pressure. Now, that external pressure, again, is quite high. Think of crossing a swift flowing stream or using water to cut metal, because it's interrupting the flow. The internal pressure actually decreases, and on the next slide we'll talk about some applications of this principle. Now, living in Kansas, you always hear about roofs being torn off in a really bad storm. Well, why is that? Well, now this goes back to Bernoulli's principle, where if something as a fluid goes faster, the pressure is reduced. So if we look at this diagram, we have a little house, and on the house there's a certain amount of pressure pressing down against the roof and a certain amount of pressure inside the house pressing up against the roof. Because remember, pressure is in all different directions, it's exerted in all different directions. As the wind goes across the top of the roof, its speed increases. As the speed increases, the pressure decreases. Remember, this is an internal pressure that you can start thinking about. If you have enough of a difference where that wind is moving fast enough, decreasing the pressure enough, that will cause the pressure pressing down on the roof to be less than the pressure pressing up against the roof from inside the house. If there's enough difference, eventually that roof can actually be ripped off. And you got to remember, it may not necessarily be a huge difference between the two, but we're also working over a very large area. This is the same idea of how airplane wings work. So next time you're in a plane, think about that. The way they have them built is that the air going over the top of the wing moves faster than the air going underneath the wing, and therefore it has less pressure on top than underneath. So we actually have a lifting effect of the airplane by just the pressure of the atmosphere.